Thank you very much, Keith, and thank you all in the audience here for attending and for supporting the Wi-Fi location topic as one of the 30-minute presentations for this WLAN Pros session. I'd also like to acknowledge the folks who are watching on YouTube, and again, it's a great resource that's available for people to learn more about Wi-Fi. So very briefly, who am I and why am I here? So I know a few of you, but obviously not most of you. So I'm Dorothy Stanley. I've been involved in Wi-Fi technology for over 25 years and been involved in the IEEE 802.11 standards arena for many of those years. I completed my third term as IEEE 802.11 Working Group Chair in March, with many other involvements prior to that. And so I'm very happy to be here today to talk to you about an application on Wi-Fi networks for which a number of standards have been developed, which, while not a fundamental MAC-PHY capability, provides a new application which provides values to customers and the ability to add new services and features in a deployed WLAN system. The remarks that I'm giving are my own. They're not a position of the IEEE or the IEEE Standards Association. The talk is divided into three parts, as you see here. First, the conclusion, the summary and benefits of using IEEE 802.11 WLAN systems for location and ranging. We'll talk about some performance numbers and ecosystem and use some interesting use cases. Okay, let's see. Am I going the wrong way here? Wow. Okay, so what is the bottom line here? Using WLAN systems for positioning and determining the location of clients or access points has been something that the technology has evolved over the past, let's say, 20 years. The fundamental technique that people started using is using RSSI. Everybody who in the audience knows what that is. I should see all the hands raised, right? Receive signal strength indication. So this is using a signal strength as a proxy for distance. And there's a certain level of granularity that can be achieved using that measurement. Generally, not the best, right? So we're talking on the order of 10 to 15 meters of accuracy, generally. You might do better, you might do worse. In 802.11-2016, we introduced a technology called fine timing measurement. And this fine timing measurement protocol was added not as a separate amendment within the 802.11 standard, but as an addition to the published standard that was delivered in 2016. And the unique attribute introduced here was the use of time, okay, as a proxy for distance rather than signal strength. And you'll see that carry forward in the additional technologies that come now and going forward. With FTM, we can get much finer resolution. So from the 10 to 15 meter accuracy level to 1 to 2 meters level accuracy. So this gives us something actually tangible that can be used for applications such as wayfinding or product finding in stores or similar applications. The 11MC, that's the code name, right? Everything has to have a letter in .11. So for the 2016 standards, it was called the maintenance standard C version. But we introduced support for the bands that were available at the time, 2.4 gigahertz and 5, and up to 80 megahertz channels. Coincident with the deployment in .11, we also worked in the Wi-Fi Alliance to make interoperability certification available. So that certification has been available since 2017. Those are the first two steps. And FTM is really the bulk of the deployments that exist today. And I'll have some examples of the deployments in a later slide. Third generation and then fourth generation. Third generation, 802.11az, introduced this use of time and measurement of time, but in a more efficient way, leveraging what we just heard about, 11ax, MAC and PHY enhancements. This allows us to get increased efficiency, increased spatial efficiency, increased number of client devices without impacting the data channel. And you see some of the other enhancements listed here. In addition, up to 160 megahertz channels are defined. We get sub 1 meter accuracy with 11az, which is really quite a significant improvement over what we have had in the past. Some of the other things are listed here. The certification here has been available since 2021. And the example that's shown here, please carefully read the decimal point prior to the 23M. In the example, which is 160 megahertz channel, 4x4, the 99% level distribution function, we get 0.23 meters of accuracy. So really quite good sub 1 meters. And then the fourth generation, which the standard is just being, is well on its way to completion, probably publication will be next year, is 802.11bk. And here what we do is extend the location capabilities to the 320 megahertz channel that's defined in 11BE. So the broader the channel generally, the more precise the ranging estimate that can be obtained. Okay. This prior slide was summary of technical capabilities and the standards that support them. Second summary slide, what are the benefits of using a Wi-Fi location, a Wi-Fi network for location and ranging determination? There are a lot of benefits. One is you have a good link budget, you can get longer range. You can find devices at a longer range from an access point because of the nature of the spectrum that you're using. We have backwards compatibility with prior generations of Wi-Fi. It's scalable to a large number of clients. The security that's needed is there. We finally have coming to market a robust solution based on Wi-Fi networks. And you'll see a lot of new applications that can be met once we have this capability in place. Okay. So, main message number one on the technical mechanisms that are used in Wi-Fi, right? Main message, and this is what you need to walk away with, is that time is a better tool for ranging than signal strength. And much of the technical challenge in doing location and ranging has to do with accurately measuring the time. It's not as easy as one might think. Okay, recall the presentation about the spectrum analyzers and identifying the exact, and I mean exact, location of where a signal begins. In the formula at the bottom, you see speed of light, c. Okay, who knows what c is? Speed of light. All the hands go up. Okay. How far does a signal go, right? How long does it take for a signal to go okay, let me rephrase that. How far does a signal go in 1 nanosecond? Okay, yes, about a foot. All right. So think about the level of time accuracy that you have to be able to measure reliably to get within a third of a meter or a foot. Okay. So it's the complexity of the implementation to do that fine, very fine timing measurement that will get the precision that we're looking for. Okay. That was main message number one, technically. So the 11MC fine timing measurement technology uses or implemented a protocol called fine timing measurement, which effectively was this ping pong mechanism to allow you to get data points from which you could measure the time that it took for a frame to go from a client to an access point, and then back from the access point back to the client, to eliminate the time of processing on each end, and then to determine, okay, how long were those signals really on the air? And that time is your proxy for distance. That is the essence. Once you have that with one access point, you can duplicate it with multiple access points and use some great math to figure out a boundary for where you are located. Okay. That's what all this complex technology is trying to do and is doing. If you get that fundamental concept, the rest really flows. Tomorrow, there's another presentation which will go into the detail on the 11MC and the 11AZ protocol implementation. So I want to give a forward pointer to Tobias in his presentation tomorrow. Okay, so this prior chart showed the essence of 11MC, essence of 11AZ. You're measuring the same thing. You're trying to measure time very precisely. And how do you do that? 11MC, we introduced MAC layer protocol fine timing measurement frames, right? What happens when you go to the MAC layer from the PHY layer? You introduce more latency. There's processing time. There's more delay. So what 11AZ did is reuse capabilities introduced by 11AX at the PHY layer. So the null data frames, null data packets, the NDP announcement frames, extensions to those frames to enable not just a single but multiple measurements and requests to come from clients in the same signal stream. So many enhancements for the basic operation of exchanging the timing measurements, along with the introduction of mechanisms for security, both at the MAC and the PHY level. So in 30 minutes, right, we're not going to go through all that in great detail. This is the high level of what's done. When you have security protocols, right, you have to get keys in place. And that's what the security context establishment does. There's a pre-association, that the mechanisms for both security mechanisms while you're associated and pre-association are defined and established, much like PMF, protected management frames. Then there's a negotiation phase, and then you actually do the measurement exchange multiple times, perhaps, and then you might terminate the session. High-level view of what the protocol is accomplishing. Two main mechanisms are introduced, non-trigger-based and trigger-based. Non-trigger-based, one end of the conversation can initiate the request at any time. I want to do a ranging measurement with U access point. I want to do a ranging measurement with the U access point, right? You can do that at any time. That's non-trigger-based. Trigger-based, we set up a schedule. Hey, Mr. Access Point, this is when I'm available. Use any of these times, they all work for me. Then I get a schedule back. And we do then the access point can look at all the clients that are asking for these ranging measurements, come up with a schedule, and much more efficient. So, and then so you've seen 11MC, 11AZ, and then, as I mentioned, the extension for 11BK. Again, what is the PHY? What are the PHY mechanisms in the header that I can leverage with the 320 megahertz channel that's defined in BE? Okay, end of section 1, main section 1 after the summary. Remember our summary, RSSI, AC, AZ, BK. Now let's say, okay, what performance are we actually seeing? The first 2 slides here I have extracted from the link at the bottom, which is a Qualcomm white paper that they published a number of years ago, I believe 2021. This is an example with Wi-Fi 5. Okay, so VHT is 11AC, 80 megahertz channels with the acknowledgments coming at 80 megahertz. And you can see that they're 90% level, at their 90% distribution function level, their measurements came in at 0.7 meters. Okay, so that's pretty good, right? 80 megahertz, so we're sub 1 meter. We're on the order of a meter. So is this real? My point is to you, yes, it's real. Okay, in this example, they did Qualcomm to Qualcomm, right? So that you know what your algorithms are on both ends, and you can get really very good performance. I call your attention to this white paper. It really is a good read. So this is just the kind of the raw numbers, right? The top line that they had in the table was 26 centimeters for average. Okay, well, that's the roughly the 50% level. Okay. Second chart from that same paper says, okay, how much better can we do with multiple measurements? It's one thing if we do measurement exchange, right? But can we further refine the data that we're getting if we have multiple measurement bursts? So we do a measurement exchange, and we do another one, and now I average the data that I get. Can I get an improved accuracy level with doing that? And the answer is yes in this example. So they went to a significant really increase. Now increase in performance. The level is 0.2 meters, where before it was 0.7 at 90%. Okay. Here's another example. The client device is blacked out. The access point is a Aruba device. And so here you see another example where here the 90% level is half a meter as a result. The 99% level is, what are we at here? 1.29 meters. So again, the message is it's real, right? The technology is coming to market, it is in the market, and it's real. Okay. This chart gives an example of, again, performance showing in a typical use case example, for example, wayfinding or finding your way in a store down the aisles, to how well the location is predicted based on the measurements. And so again, you see really very good performance, 90% level of just over half a meter. I mentioned Wi-Fi Alliance and the Wi-Fi Alliance interoperability certification being available. The interoperability certification, the main focus is on, do the two ends interoperate based on the protocol as the protocol is defined? Generally, performance is not the primary focus of the test. Can these two devices talk to each other and exchange the protocol properly is the main focus. In addition to that certification program, We've conducted 10 next week, interoperability events for location. This provides an opportunity for vendors to bring their equipment in, test with their counterparts, and further refine their location algorithms. Now, recall back, why would I need to refine my location algorithms or my the points at which I'm actually measuring when the signal comes in, all right? Recall our conversation about the use of time and the difficulty of accurately, precisely measuring that time, right? So there's a lot of work to be done and a lot of work that has been done to help vendors to refine their algorithms to get a better estimation. I just wanted to go back here. So here, as an example, you can see the variability in some of the numbers, right? So this is the error that I see. And so by analyzing this data, refining the algorithms, you can further improve the performance. Here's an example from July 2023 interop event, another example with Qualcomm, and they agreed to have this data shared. So this is, again, 5 gigahertz, 160 megahertz channel, and shows the difference between using a 4x4 system versus 1x1, and the improvement that you get in the 4x4 system. So again, main message, the technology is real, and the performance really is very good. Okay, end of second part of presentation. Third part of presentation, what are some use cases? First of all, what's the ecosystem, right? Somebody talked about, well, I have this, when I'm deploying MLO, if I deploy MLO, I have lots of pieces that need to come into play so that the feature actually is accessible up the stack. Very, very similar situation with location. So first of all, I've been involved in standards for a long time, right? I have to show the standards chart about 802.11. So 802.11, where do we fit? Do we define application level protocols? No. Do we define these other protocol levels up the stack, network, transport, et cetera? No. We happily leverage everything that the IETF does there. What do we focus on? We focus on the MAC and PHY. And this is largely true across all of the 802 groups. Call out for time-sensitive networking, a lot of work that's being done in 802.1 that we're trying to leverage going forward in .11 as they've done in .3. So our focus is MAC and PHY. Now, what does that mean when we ask about what does it really take to implement indoor location? Is it just the MAC and PHY? Who says yes? Good. Who says no? Okay. It's not just the MAC and PHY. We could have MAC and PHY technology all day long. The user will never see it. You need changes by the chipset vendors, you need changes in the access point, you need changes, and this one took a long time in the OS vendors, right? And then you need the applications on top of that. And potentially you'll have the cloud applications and larger deployments. But the red check marks here show really what is deployed today. Okay. Here are some examples about support of the technology in deployments and by some major industry players. So you see, we've had examples with Walmart, Home Depot, these large, big box stores. And they continue, why? Why are they looking for this, right? What motivates our end customers, right? We're not doing this just because we can do it. We're doing this because it provides value to the end customers. They can save money. They can be more efficient. They can reduce waste. They can track different sets of equipment. So that's why we're doing it. And there really, really, really is a demand for this across the board. So HPE, Aruba, we announced our support for both 11MC and 11AZ now in Wi-Fi 7. Cisco has also announced support. And the goal is to just build on this momentum and get more and more implementations out there. All right. So use cases, here are some examples. So public domain, you can have find your way in a store. One example that has been used frequently is how many people have ordered groceries to be delivered? Yeah, right. Costco, right? Order Instacart, get stuff delivered. Okay, well, what does that person have to do who's pulling your order? Right? They have to look at your list, and they have to navigate around the store to fill your basket, right? They can do that navigation efficiently, or they can take 2 hours, right? So what's best? They should do it efficiently. And so the retailer can pre-establish a pick list, okay? This is the most efficient way to pick up all the groceries that Joe has ordered as I walk my way through the store. And that can all be done ahead of time so that the person who's actually picking that order will do it efficiently. There's studies on this, believe it or not, right? So there's a need to know, and that you want to know, okay, how do I navigate through the store that way? A lot of enterprise use cases, indoor navigation, et cetera. Proximity, you want to know, you turn on your light or whatever, well, which one? Am I close to it? I have some more examples later. And one that is coming, this last one, secure access. What if the consequence of making a decision to do something based on location is associated with a really high value? Like, if I come here and I have my phone or whatever, I want to turn on the laptop, right? The laptop is presumably open, but it would log in for me, right? That's a high value use case, because what if the wrong person opens it up? Or your car, or your house, or something like that. And in 11AZ, we introduced not only MAC layer security, but PHY layer security. And so that physical layer security, which is virtually impossible to attack, is the foundation of the solution for this particular use case. And we're targeting that for the end of 2024. Okay, next couple slides, some examples of tools that are out there if you want to play with. So I see before me, and on YouTube I'm sure, people who love to tinker, right? You just want to play with the technology, right? You just have to get your hands on it. And here are some tools developed by Google that will allow you to play with the location technology. If you have an Android-based device, you have the ability to use these tools. You have the technology implemented in those devices. This slide is here because there's a link to a YouTube video, which was developed by Google, that will show actually the navigation within an indoor location, and show you how just like if you're driving, you go the wrong way, then it adjusts and it tells you which way to go. That's another link. Okay, that we talked about. New use cases. So customers will find more use cases for location. Once you have the location capability there, you will find use cases. In fact, almost serendipitously, we realized when 6 gigahertz standard power AFC location requirements came through, it would be really useful to have the access points self-locate, right? And so, what can we use for that? Oh, well, here, we have Wi-Fi location. So we've done that. We're looking at extending this to emergency services. And I was talking to a guy at a conference last week. He talked about, well, this would be really handy to have for connected tools. He wanted his connected screwdriver. The cloud wanted to know where his connected screwdriver was so that it could tell which side of the car had been processed or not. So, you'll find these applications. And then finally, Again, the audience before me wants to know more. You want to dive deeper and really understand it. Here are some resources for you. I highly recommend the two that are in bold. The first is a Signal podcast, Wi-Fi Alliance podcast, that was done by Rolf de Vecht of Qualcomm. He talks about the technology, some use cases, and the white paper is referenced there. Please read the white paper. And then the second one, Klaus is here for Klaus puts on this Wi-Fi Now event. So about a little over a year ago, Jonathan Segev and Roy Want gave a tutorial on Wi-Fi location. It's 3 hours long. That's the caveat, it's 3 hours long. However, you will learn a lot. I highly recommend it. Jonathan works for Intel. He was the chair of 11AZ and 11BK task groups. Roy Want works for Google. Long time, both academic and practitioner in the area of location. He served as the editor of those two amendments. Very, very knowledgeable guys. So with that, that's my presentation. You have some information now, and you have some information later. And I hope that you'll see widespread deployment of Wi-Fi-based location services going forward. And I thank you for your attention.